Today I'm going to tell you about film surface expansion in correlated metals with strong ferromagnetic spin fluctuations based on cluster extension of dynamical mean field theory, cellular DMFT, and dynamical vertex approximation, D gamma A. So my name is Ryotaro Arita from University of Tokyo and Riken. And this work was done in collaboration with Yusuke Nomura, who is now in Keio University, but very big news from Japan is now he's moving to Tohoku University, one of the 7 prestigious national universities in Japan, as a full professor. So he's going to make a very big group in Sendai. So as far as I understand, the group of his group will be very large as 300 or 400 square meters. So there will be plenty spaces for guest researchers. So if you have a chance to go to Sendai, it's just 1.5 hours from Tokyo. So please visit his group. And Motoharu Kitatani from University of Hyogo and Shiro Sakai from Riken. So this is a brief outline of my talk today. So today I'm going to discuss film surface expansion in correlated ferromagnet. And so first I would like to start with introduction or explanation of the motivation or the background of this project. And I'd like to introduce some relevant experiment. And then I'm going to show 2 results. One is our calculation results for 2-orbital Hubbard model based on cellular DMFT. And this is a representative result. So this is results of the CDMFT calculation. And green line is a film surface of non-interacting case. And when the correlation is not so strong, then the film surface looks like that of non-interacting case. But when correlation becomes a bit stronger, then film surface tend to expand. And this is similar to that of a film surface of free polarized state, or the film surface of majority spin of ferromagnetic states. And we found that this observation, this behaviors can be observed also in the single orbital Hubbard model, the simpler model, by the D gamma A calculations. So this is the white dashed line in the film surface of non-interacting case, and the red one is the film surface of obtained by D gamma A. Then again, we see that the film surface expand. And so this is similar to that of a fully polarized state. So this is the take-home message of my talk today. Okay, so let's start with the introduction. So in correlated metals, we often observe the film surface reconstructions. And the very famous example is that in cuprate. So this is the phase diagram in the plane of temperature and the carrier doping. And there is a pseudo-gap phase here. And so these are the spectral function obtained by ARPES. And if you look at the spectral function of the pseudo-gap phase, we see that the intensity at pi 0 or 0 pi, it's very weak. And so we have the so-called film arc spectrum. And this is quite different from that of non-interacting film surface. And so this film arc spectral function can be actually obtained by or studied by cluster extension of dynamical mean field theory. So if we employed cluster extension of DMFT, then we can have a momentum dependent self energy. And so here epsilon is one body dispersion. And so if we calculate the Green's function of self energy of a two-dimensional Hubbard model, then we can study the momentum dependence of self energy or Green's functions. And so this is a result of the CDMFT calculation and the 5% whole doping. And so if you look at the imaginary part of the self energy, the function of mass bar frequencies, and if you look at the self energy, the lowest mass bar frequency, we see that so when the Coulomb interaction U becomes stronger, then imaginary sigma diverges. So this makes zeros of the Green's function in the momentum space. And if we plot the Green's function as a function of imaginary time, and if we look at tau equal half beta, then we can pick up the information of film surface. And then we obtain so-called Fermi arc here. And this is corresponds to this. And so this calculation is, of course, the case when the antiferromagnetic spin fluctuation is strong. Then the question which I'm going to discuss is what happens in the case when the ferromagnetic fluctuation, spin fluctuation is strong. And so concerning the spectral function of the ferromagnets, conventionally, we expect that the change of spectral function can be described in the so-called Stoner theory. So when the system has a ferromagnetic long-range aura, then majority spin and minority spin, the different spectral functions. So this is majority spin, and this is spectral function of minority spins. And between these, we have the energy splitting. This is exchange splitting. And when the system experiences from ferromagnetic to paramagnetic phase transition, then this splitting disappears, and we obtain this paramagnetic spectral function. And so there are many ferromagnets which follows the spectral function can be understood in terms of the Stoner theory. So one typical example is cobalt shandite. This is a very hot ferromagnet now because it shows a very large anomalous transverse transport. This is anomalous activity. So here I am showing the crystal structure of cobalt shandite. So cobalt atoms makes a Kagome lattice. And this is a band structure obtained by the standard LSDA calculation. And this is a band dispersion of majority spin, and this is a minority spin. And one interesting feature of this material is that so we have band crossing across the film level. So this is the so-called wild nodes. And due to this, the existence of this wild nodes, so if we calculate the Berry curvature, Then around the film level, it becomes large. And so if we calculate anomalous conductivity, then so this is a plot of anomalous conductivity as a function of chemical potential. And we see that it is larger than 1,000 Siemens per centimeter. It's quite large value. And for this material, actually, so LSDA works quite successfully. So, for example, for this anomalous conductivity, so recently the group of professors Sokura and Iwasa, so they succeeded in intercalate lithium ion between cobalt layers, thin layers, and they can introduce many carriers. And they measure the anomalous conductivity, and they superposed the theoretical value here. And we see that agreement between theory and experiment, very good. So this indicates that the band structure obtained by LSDA it captures the qualitative features of the real materials. And indeed, so ARPS measurement also performed. And so this is the comparison between the LSDA and the ARPS measurement. And so Liu and others, they measure the spectral functions as a function of temperature. And so the system becomes a paramagnet here. And so also, both in the case of ferromagnet case and paramagnet case, the agreement between theory and experiments are very good. And here in this plot, they plotted the size of exchange splitting, so the energy difference between the majority spin and the minority spin as a function of temperature. And we see that this energy splitting disappears at TC. So for this material, Stoner picture explained, or we can understand the spectral functions in terms of the Stoner theory. But on the other hand, some materials, the Stoner picture doesn't work well. So one example is an strontium lucenate. And so this is a crystal structure of strontium lucenate, and this is a schematic pictures of film surface of this material, paramagnetic phase and ferromagnetic phase. And so here, so they looked at the energy splitting of majority spin and minority spins, alpha bands, around here, gamma to M, yeah, around here. And so they plotted this energy splitting as a function of temperature. And simultaneously, they measured the magnetization, the red curves, and also spin polarization at the gamma point. So this is a spin resolved ARPS measurement, so they can look at the spin polarization. And for spin polarization and magnetization, those two disappears at Curie temperature. But on the other hand, for the band splitting survives at TC and even above the TC. So even above TC, the system is paramagnetic, but still energy splitting survives. So this behavior cannot be understood in terms of the Stoner theory. And these behaviors are also studied theoretically. And so here I'd like to introduce one pioneering work by Andrei Katanin and his collaborators in 2005, so almost 20 years ago. So in this paper, Andrei and his collaborators studied the two-dimensional Hubbard model with a very strong ferromagnetic instability. And they studied the Hubbard model by the two-particle self-consistent approximation or functional renormalization group or word identity approach. So they obtained the self-energy and vertex collection using word identity. And by these three approaches, they calculate the spectral function. And so they found that, so they studied a two-dimensional system. So due to the Marmin-Wagner theorems, at finite temperature, the system doesn't have a long-range order, but at finite temperature, if the temperature is low enough, sufficiently low, then the spectral function has a two-peak structure, like an exchange splitting. So although the system doesn't have a ferromagnetic long-range order, the spectral function can have a two-peak structure. So this is a schematic picture of their results. So at t equals 0, so the system is ferromagnetic. So upspin and downspin has a different spectral functions. And at finite t, so there is no long-range order. So if we follow the Stoner theory, then we expect that this exchange splitting disappears. But so Andre and his collaborators found that when the temperature is low enough, then so both upspin and downspin have the same spectral function, but it has two peaks, just a superposition of this upspin and downspin spectral function. So here, so in the phase diagram, we have a quantum disorder state and a quantum critical state and a renormalized classical regime. And so Andrea assumed that the system is the case when the system is far deep inside this renormalized classical regime. So the spin correlation diverges as a exponential t star over t. So in such a situation, they found that the spectral function can have this type of behaviors. So this is a result for the single band Hubbard model. But on the other hand, they studied this problem for a two-dimensional Hubbard model with next nearest neighbor hopping T prime. So when T prime is as large as 0.5, and then the Van-Hoff singularities moves to the bottom of the band. And in this case, when the density is low enough, then ferromagnetic spin fluctuation becomes very strong. So this problem has been studied by many people, for example, Carsten Honakamp or Andre Katanin, and actually Carsten Held and myself also interested in this system. And in 2006, we pointed out that there is an possibility that triplet superconductivity can be dominant when the spin fluctuation becomes very strong. So this phase diagram was obtained by dynamic cluster approximation, right? So here we do not go into the possibility of superconductivity, but just look at the normal state. But anyway, so for this system, when the density is low, the ferromagnetic instability becomes very, very strong. And so this is a spectral function obtained by a functional renormalization group. And Andre others discovered that when the ferromagnetic fluctuation is strong, then we have a pseudo gap, and so double peak structure appears around the Fermi level. And this is a result for the word identity approach. So they consider the self-energy collection and vortex collection. And so assuming that the system is far inside the renormalized classical regime, and also they introduce some approximation that assuming that the number of the transverse spin mode is large enough, then they derive a very simple expression of self-energy. And if we plug into this self-energy in the Green's function, then we can show that spectral function is a summation of spectral function of non-interacting case with minus delta energy shift plus delta. So these structures. And so these are the analysis for single band Hubbard model. And recently we studied this problem for two orbital Hubbard. So in the multi-orbital systems, then in the interaction part of the Hamiltonian, the several channels, namely intra-orbital Hubbard U or inter-orbital Hubbard U, Hunt coupling, spin flip terms, and pair hopping terms, and so on. And then, so in the presence of Hunt coupling, so the multi-orbital system, the phase of the so-called Hunt metal. So Hunt coupling J as the so-called Young's effect, two effects. So one effect is that so it reduces the size of Mott gap and increase the size of critical UC. And then the other effect is so Hunt coupling can maximize the size of local magnetic moment and suppresses the coherence temperature. So this is a very famous phase diagram in the plane of interaction and the number of electron sites. And we see that there are wide, strongly correlated region away from integer fields. So, so it is in these questions when the ferromagnetic spin fluctuation is strong. So in this Hunt metal phase, how the spectral function looks like. So we studied this problem by 2x2 cluster DMFT calculation. So this cellular DMFT calculation becomes a challenge for a multi-orbital system, but USK made a very efficient code, and we performed these calculations. So we studied the two-dimensional square lattice and assumed that the two orbitals have the same dispersion. And the dispersion, this is the same as that studied by Andre. And so we do Hubbard U, and we calculate the spectral function for paramagnetic state. Okay, so let us move on to the results. And so first, we look at the case when the density is 1.9. So please note that so we have two orbitals. So the half filling is at 2.0. So we slightly dock holes. And so this is a result of the cluster DMFT calculation for two orbital system, the imaginary sigma and the real part of the self-energy. And this is a result for a single one model. And so the behavior is very similar. So if we if the interaction becomes stronger, then the imaginary sigma becomes stronger around pi. And so this makes the zero of the Green's function around pi. And then, so if we look at the Green's function at tau equal half beta, then the so-called Fermi arc appears. So this is the result when the antiferromagnetic spin fluctuation is strong. And then let us move on to the case when the ferromagnetic spin fluctuation becomes strong. Actually, when the density becomes lower, then ferromagnetic fluctuation instability becomes stronger and stronger. And in this situation, so if we look at imaginary sigma again, then we see that imaginary sigma becomes stronger and stronger at the gamma point, not pi pi. And in this case, so this is an the Green's function at the tau equal half beta. And so green line is the film surface of non-interacting case. And so we take the ratio of J over U. J is front coupling, U is R value. It's 1/4. And then when U is 8, then the film surface is similar to that of no-interacting case. But when the U equal 12, then obviously the film surface becomes larger. And so this is the spectral function. So this is a dispersion, band dispersion of non-interacting case. And this is the band dispersion of fully polarized case. And so we see that the result of cellular DMFT it looks like that of fully polarized band dispersion. So it should be noted that in our cellular DMFT, we assume that we calculated paramagnetic case, but the spectral function looks like that of ferromagnetic case. And this is a plot of the change in the density momentum. So this region is the original, film surface, and this region, so the number of electrons decreases. So in non-interacting case, it's a free field, but the number of electrons decreases, so it becomes almost half filling. And this region, the density becomes increases. So the charge moved outside the film, original film surface. Original means a non-interacting film surface. And so if we calculate the spectral function using the self-energy proposed by Andre, then so we have two peaks. So which corresponds to minority spin and majority spin. And if we compare these spectral functions, there is similarities and differences. And one commonality is that so this majority band, so it's almost the same. But for the minority band, in our cellular DMFT calculation, the spectrum becomes very broad, and we can see the bands which corresponds to the minority bands. And the band structure is almost the free field, free polarized band. Okay, so this is what we observed for two of the model. And then we studied whether we can observe this behavior in the single band Havana model. But we found that in the case of a single band Havana model, we didn't observe the film surface expansion. But it should be noted that in the case of Andre's calculations, so he assumed that the system is far inside of the classical renormalized regime. So spin correlation length is diverges. But in the cellular DMFT calculation, long-range spatial correlation is not considered. So we decided this problem to study this problem by a dynamical vertex approximation. And Motoharu Kitatani performed an extensive calculation for a single band Hubbard model and TT prime Hubbard model, the same model which was studied by Andre Kitani. So this is T prime, and this is density. And we see that, for example, in this case, so this white dashed line is a film surface of the no interaction case. And so this is the result of D gamma A. So we see that the film surface expands. And this behaves as more visible. And so this is the peak of the spin susceptibility. And so we see the spectrum becomes sharper and sharper. And so film surface expand. And at U equal 40. And if we compare the bounded film surface of free polarized case, so agreement between the D gamma A and this free polarized state is very good. So this is temperature dependence, and so we see that at high temperature the spectrum is broad, but at low temperature, so we see a clear film surface, and it's almost that of the free polarized. And so this is a U dependence at smaller U. So in the FRG calculation by Andres, he observed the splitting, but in our D gamma A calculation, it's not so clear. But for larger U, so we see an intensity around the gamma point and also here. So this is a kind of two peak structure. And when U equal 8, the film surface becomes clear. So this is the situation, I think, Andres considered. So this small surface, which corresponds to the minority spin, is here, and the large one is here. So it's not so clear, but the situation is very similar. Okay, on the other hand, so Motoharu also performed the flex calculation, but in the case of flex, we didn't observe a clear expansions. The spectrum is always broad. So if we compare the flex and the D gamma A, we see that. So in the case of D gamma A, the spectrum is very sharp here, but in the case of flex, it's broad. This is consistent with the observation of Andre. So if we neglect the vertex correction and just consider the self-consistent self-energy, then we have always have a broad peak, one peak, no splitting. Okay, so this is a comparison, again, comparison of C DMFT and D gamma A. And in the C DMFT, so long range spatial correlation is not considered, so we didn't observe splitting, but in the D gamma A, we consider long range spatial correlations, and we see a film surface expansion. Okay, so let me conclude. So we studied the film surface expansion in correlated metals with strong thermomagnetic fluctuations. And in the case of two orbital Hubbard model, so we have a Hund coupling, and due to the Hund physics, and local spin becomes larger. And in that case, we observe film surface expansion. So this film surface is almost the same as that of free polarized state. And in the case of single band Hubbard model, so CDMFT doesn't observe film surface expansion, but in D gamma A calculation, we observe expansion of film surface. And so we think that the long range spin correlation is very important to observe this. Okay, thank you very much for your attention.
Thank you very much, Ryotaro. We're now open for questions. I think Karsten had a question first.
Yeah, thank you very much, Rio. Very nice talk. I wonder, so this opening of the gap you described in Andrei Katanin's work and in your work, you can have it both from mod physics. So if you have a mod insulator and the magnetic order goes away, you could have such a splitting and also then possibly this thermal surface enhancement. But you can also have the opening of the gap due to spin fluctuations. So how is it in Andrei Katanin's calculation and in your calculations?
So when the spin correlation diverges, then actually we can derive an expression like this.
So delta zero is the spin correlation scale and not a U or something like that in a mod insulator, where you could have similar kind of physics.
Yeah, kind of exchange spreading.
Okay.
And yeah, once we obtain this, then we can obtain this spectral function. And this is, yeah, I think, so, yeah, although in our numerical calculation, this spectrum is always very weak and broad. And that is a difference between Katanin and Ray's calculation and our calculation. So, for example, this. So if we plug in, you use this self-energy, and then so both minority spin and majority spin, the clear spectrum, but in our calculation, this part is always broad. And also in the gamma A calculation, this is broad. It does not make a clear small film surface. That is the difference. But we think that the physics behind it is similar in the case of single band Haber model. And multi-orbital Haber model, we think that front coupling J is important. And although we do not introduce long-range spatial correlation, we can have this spectral function.
Okay, thank you.
Large local moment is formation of large local moment is important in multi-orbital system. And in the single band Haber model, so we think very low density region, so the local spin is not so large. But once we consider the long range spin correlation, then we can have a large film surface expansion.
Okay, thank you.
Okay, thank you. Next we have Antoine.
Yes, thank you, Rio. That was a very stimulating talk. I think I understood the point you are making in the case of Hund coupling and ferromagnetic fluctuations. So my question will be going back to the single band case where the physics is different, right? So I would like to make sure whether you agree or not on the following points. If I look at the single band model, say Hubbard model, but in the vicinity of half filling, not low density, okay?
Yeah.
So as far as I know, if I look at that model in a relatively high temperature regime, let's say temperature of order half of the hopping, the physics of the expansion of the quote-unquote Fermi surface, of course, this is a fuzzy notion which is defined by the maximum of the spectral function. But this expansion is there, and it's been seen in many calculations. In single-side DMFT, it's there, it's determinantal Monte Carlo. Everybody agrees on that, right? We agree with that, right? Now,
Yes, yes.
if we ask the question how that evolves as we go to lower temperature, well, of course, in that regime at lower temperature, we form a pseudogap. And then what can happen, and this has been seen in DCA calculation very clearly, is that the Fermi surface, which would be nominally, say, electron-like, because we are hole-doped, would actually reshape into something which is essentially hole-like, namely the arcs, are inside the antiferromagnetic Brillouin zone. And so the Fermi surface is profoundly modified by the correlation effects in that regime. Right. I guess, do you have T prime? But here you have T prime, right?
Yes. Always we have T prime.
Yeah, but so I guess what I'm saying is that when T prime is 0, where the Fermi surface would be nominally electron-like, it can be reshaped into hole-like, and this effect becomes weaker as you increase T prime.
So are you talking about small T prime and cross the half filling?
Yes, let's say even 0 T prime. Yes.
0 T prime and cross the half filling.
Correct.
And so what is your question?
No, the point I'm trying to make is that at high temperature, the expansion of the Fermi surface is indeed seen.
Yeah.
But as we go to low temperature, it's even a more drastic thing that the in cluster DMFT or DCA or probably every calculations, the Fermi surface can become essentially hole-like. So there is not only a change of, there is a change of topology as compared to the, that's the point I'm trying to make. Yeah. The thing, I have another question actually on exactly on the plot panel A of your slide. I'm a little confused about the following, because if I look at your K momentum path, when I go from 0, 0 to pi 0 to pi pi on the right, I see a very big im sigma, which corresponds to the suppression of the spectral weight at the antinodes. Okay, this one, yes.
Yeah, so this divergence makes a 0 Green's function around here. So
I see, but I should also see, but if I move now from 0 to pi pi on the diagonal, which is the left part of the plot, right? Yes, like this. Yes, here. I should see, so you are saying the line of 0 is still present behind the Fermi surface, that's the big value?
Yeah. So as far as I said, this makes zeros of the Green's function. Yeah.
But the thing that I find striking is that the imaginary part of sigma should be smaller than the corresponding value at the antinode, right? Because I see a bright node. And it's not so clear on the plot. But
here?
Yeah, here the spectral function, the imaginary part of sigma is expected around pi over 2 to be rather small. That's what I'm trying to say.
Yes. So
I don't see that on the
make
plot.
poles here and zeros here.
Yeah, but so to have a pole in sigma has to be small.
So you say that it's not clear from this plot?
Yes, that's what I'm saying. I would expect it to be smaller.
So that's yes. Maybe Shiro Sakai can answer this question. I'm sorry. But yeah,
no problem. We can discuss that offline as well.
Maybe we should take one or two other questions because time.
Absolutely.
Yes. So in the Q&A.
No, go ahead. Yeah. So there is a question by Waiting Ling. Can you ask the question?
Yes, thanks. So I'm just curious. So from this point of view of Lottinger theorem, the Fermi surface is
that is the theorem. So that is also I'm interested in. But yeah, so my naive understanding is that so when the film surface expand,
Yes.
so which one? Anyway, so in this case, I expect that there is a Green's function 0 region here,
Mm-hmm.
and that allows the system to have a larger film surface. But this is not confirmed numerically, not yet. This is the scenario why we have a larger film surface.
Okay, so you mean the particle distribution would be changed in the interior?
Yeah, around the gamma point, the film the self energy diverges. So some things happens around the gamma point. So I expect that so not yet confirmed, but I expect that some things happen around the gamma point, and that allows the system to have larger film.
So I think it's an interesting question to explore this. Okay, thank you.